fourth and final section, we're going to look specifically at gases. And we're going to look at some of the key properties of gases, along with some of the gas laws associated with how gases behave. So what are some of the properties of gases, and how can we predict the effects of pressure, temperature, and volume on a gas? So we'll start with properties. One of the things that we know about gases is that they tend to fill whatever container they are in. They spread out easily and easily mix with one another because there's a lot of space between their particles. For that same reason, they have very low densities and they are compressible. Most gases are very little matter and a great deal of space. So they are mostly empty space. Gases are able to exert pressure on their containers, however, because as the particles move around, they collide with each other and they collide with the walls of their containers. So we can look at gas laws to help us predict the behavior of gases as it relates to pressure, temperature, and volume. So the gas laws are going to help us to predict this. So we say that gas laws are the laws that state the mathematical relationship between volume, temperature, pressure, and the quantity of a gas. So we'll start with the first one. It's called Boyle's law. Robert Boyle was an English scientist who spent a lot of time working with gases, and eventually he came up with this law. For a fixed amount of gas at a constant temperature, the volume of a gas increases as the gas's pressure decreases, and the volume of a gas decreases as the pressure increases. That is assuming that we don't change the amount of gas in the container. So if we force the same amount of gas into a smaller container, we will find that it will have a much greater pressure. That is really Boyle's law. Mathematically, pressure 1 times volume 1 gives us pressure 2 times volume 2. If you take a look at the diagram on the right-hand side and you look at the astronaut's suit, you can see that the y-axis is pressure and the x-axis is volume. So the red line shows as pressure is decreasing, volume is increasing, meaning that there is less pressure on the outside of the suit. So if we were to go into outer space without a pressurized suit, because the pressure outside of our suit would be very, very low, the volume of the suit would increase by a lot. So how do we work with Boyle's law? Well, Boyle's law, P1V1 is equal to P2V2, essentially means that we're always going to multiply pressure and volume and divide by pressure or volume. And it's important to pair them correctly. So pressure 1 with volume 1, pressure 2 with volume 2. Typically, they will give us an initial combination, so our ones, and then we will divide by the new pressure or the new volume to find what we're missing. So if we take a look at this, the gas in a balloon has a volume of 7.5 liters at 100 kilopascals of pressure. The balloon is released into the atmosphere and the gas expands to a volume of 11 liters. So if we assume that the temperature doesn't change, what is the pressure on the balloon at the new volume? So we know that higher in the atmosphere there is less pressure because there is less air, but how much is the pressure different? So we know volume 1, pressure 1, and volume 2. So if we rearrange our basic equation, to solve for our new pressure is to take P1 times V1 and divide by V2. So when we insert the values that we know, 100 kilopascals times 7.5 liters, if we divide by 11 liters, we get an answer of 68 kilopascals. The second gas law is called Charles' law. Jacques Charles was a French scientist who spent a lot of time working on gases and ultimately discovered there was a relationship between the volume of a gas and its temperature. So his law says that for a fixed amount of gas at a constant pressure, the volume of the gas increases as the gas's temperature increases, and the volume of the gas decreases as the gas's temperature decreases. So this is a direct relationship. As one goes up, the other goes up. So we have a little bit different mathematical law with V1 over T1 equal to V2 over T2. So you can see on the right-hand side, the balloon is full volume because it is at room temperature. But when you pour some liquid nitrogen onto the balloon, because it has a very, very low temperature, the gas inside of the balloon cools very quickly and its temperature drops. And as its temperature drops, its volume also drops, and we see the shrinking balloon. It's important to note that anytime we work with temperature and gas laws, that we work with a Kelvin temperature. Now, this is very much like working with Pascal's principle in that we're going to cross multiply and divide. And the third gas law is Gay-Lussac. Gay-Lussac's law relates pressure and temperature when the volume is held constant. So it says that the pressure of a gas increases as temperature increases if the volume does not change. The pressure decreases as temperature decreases. So it's very much like Charles' law, except using pressure instead of volume. So again, we will cross multiply and divide, and we must work with Kelvin temperatures in order for this to work. But you can see an example of this here on the right-hand side. If you have a cold tire and you check the air pressure of the tire, you might get a pressure of 200 kilopascals. But after you have been driving, the friction between the tire and the road causes the gas in the tire to warm up, and with that higher temperature, the pressure has risen to 220 kilopascals. That's very, very common. Pressure is very, very changeable with temperature, just like volume is. It's the reason why if you check the outside of an aerosol can, like a can of hairspray or spray deodorant or Axe, that it says do not incinerate. The word incinerate here means don't throw it into a fire. Maybe you already know what happens, and I hope you don't know it by experience because it's extremely dangerous. But if an aerosol can is thrown into a fire, the increase in temperature causes the gas particles to move very, very fast and collide with the walls of the container of the can. And eventually, the walls of the can are not able to withstand the pressure, and the can explodes. As I said, it can be very, very dangerous. Gay-Lussac's law is also the reason for a can of hairspray to feel cold after you have sprayed some of the hairspray out. If you feel the can, you can feel that it has lowered in temperature. Inside of the can, after you spray some of the gas out, the pressure is lower, and therefore the temperature is lower as well.